Okay, thank you all for coming. It's really nice to be here. So I was really generously allocated an hour because I'm doing a little sort of introducing some concepts that I think are going to be important in the future, and I'm not sure everybody in this room has seen before, but I'm hoping not to use the whole hour and hoping we can have a little bit extra coffee time. But please interrupt me with questions from the room, or I guess we can wait till the end for questions from Zoom unless there's something urgent. So. Awesome. So I really come from the algorithms community, and I've had the privilege of working with Gautam and Mahbod over the last year or so on some new approaches to algorithm design in differential privacy. And so I want to share some of those concepts with you. And then the talk after me, Mahbod's going to discuss in a little bit more detail one of the applications of these ideas. So the starting point for this talk is the exponential mechanism, which I probably don't have to introduce in this audience. We'll review it later, but the exponential mechanism is, the core tool for pure DP algorithm design. Core in the sense that it's complete for pure DP mechanisms, right? Every pure DP mechanism, if you take the log probability, you can view that as an instantiation of the exponential mechanism. So it's like the most powerful tool for pure DP mechanism design. But it has a drawback, which is that in settings where you have a lot of potential outputs, like an exponentially large number of potential outputs, and you need to define some exponential mechanism over that exponentially large set, it often leads to computationally intractable mechanisms, it leads to distributions, probability distributions that we don't know how to sample from in polynomial time. This is especially true in one of the application areas that I'm most interested in, which is high-dimensional statistics, where often your output will be a vector in a high-dimensional space, like a regression vector, or a matrix, like a covariance matrix, or a matrix that you completed the entries of, or whatever. These are high-dimensional objects that you need to output. So just for a very brief review, what is going on in the exponential mechanism? Well, you have this fancy thing, cool. You have some input data set X that consists maybe of a bunch of individuals. You have some space of outputs Y. And to instantiate the exponential mechanism, all you need is a score function, which assigns real valued scores to pairs data set, comma, output. And the ultimate algorithm, once you have this, if you want an epsilon differentially private algorithm, is that you will, given the data set X, you will output a sample from the following probability distribution, where the probability of a given output is proportional to X with epsilon times the score. I'm going a little quickly because I think people know this. And to establish the important properties of this mechanism, what do you need? Well, you'd like it to be private. And for privacy, you can phrase privacy as a property of the score function. It's a simple bounded differences property of the score function that if you have two neighboring data sets and any particular output, the score only changes by 1. And you'd like to prove some utility property. The utility property is that, well, the mechanism is basically, I'm throwing away some constants and stuff, but it's basically guaranteed to output a Y whose score is at least that of the optimal Y minus the log of the size of the output set over epsilon. You can replace this with a volume or something if you're in continuous space. And to really, okay, so that's something formal, but to make the thing work, you would like that a Y that has this score for a given data set is somehow good for your application, right? It's an output you like. So that's our brief review of exponential mechanism. And now let's return to this issue that the sampling problem that you get if your score function is complicated is some complicated high-dimensional sampling problem, right? So, and often it's not a priori clear how you would sample from this distribution. Let me point out, first of all, that what non-theory algorithm designers love to do, which is just, okay, you don't know how to do some hard problem, we'll throw some heuristics at it. It's not allowed here, right? Because you're not allowed to use a heuristic sampling algorithm because you'll lose your privacy guarantee. So not only do you have to develop a good sampling algorithm, you have to prove that it actually accurately samples from this distribution. So what do? Well, you could hit your head against it really hard and try to design some clever, computationally efficient sampling algorithm for the particular instance of exponential mechanism you have. Maybe that works, maybe that doesn't. Or you could throw up your hands, forget exponential mechanism, and just do something else, right? Use one of the other or several of the other tools in the privacy toolbox, Laplace mechanism, Gaussian mechanism, and maybe these things involve relaxing your privacy guarantees to approximate or or CDP or whatever. But these have drawbacks as well. So, the first is not always possible. And the second, it's not always clear when other tools will lead you to a mechanism with the same privacy accuracy or privacy utility trade-offs as you can get out of the exponential mechanism, right? So these can lead to interesting algorithms, but it doesn't always get you what you want. So today's talk is about a new perspective on addressing, or what I think is a new perspective anyway, on addressing the intractability of the exponential mechanism. We call this perspective or technique the sum of squares exponential mechanism. It's named for this sum of squares method, which is a powerful algorithm design technique coming from the area of convex optimization. And I'm going to tell you about later in the talk. And so far, so this is something that we worked on over the last year or so, or maybe a little bit more. And so far, we know of two significant applications of these ideas. In this paper with Gautam and Mabod, we gave the first algorithm, DP algorithm, that runs in polynomial time and has nearly optimal sample complexity for a very basic high-dimensional statistics problem, which is estimating the mean of a probability distribution from independent samples. It turns out that every previous polynomial time algorithm for this problem had sample complexity that was off by dimension factors. And in upcoming work with a PhD student at MIT, Christian Georgiev, we've applied some of these ideas to do sparse mean estimation, so to bring sparsity into the fold. But I think that this is just getting started, and I think this is going to be a major technique for polynomial time DP algorithm design in the future. So let's start with like a 10,000-foot view of SOS exponential mechanism. What can it let you do, at least in the form that we understand it right now? And I don't want to claim that this is the ultimate form of this tool. We're just starting to understand what we can do. So let's suppose that you have in your hands some exponential mechanism, some DP mechanism based on exponential mechanism. And the output space, I'm just going to assume, is convex. Okay, so it's some high dimensional, lives in some vector space, let's say, and then the set of outputs you're interested in is convex. Now, here's the thing, here's the basic requirement of SOS exponential mechanism, and it's going to seem opaque right now, and we'll lower the opacity throughout the talk. Suppose that you can prove these two important properties that you need for exponential mechanism to work, that you can prove the privacy and utility guarantees of your instance of the exponential mechanism. You can prove them in a certain restricted proof system, known as the sum of squares proof system. So you don't get to use all the tools of mathematics. You have to tie your hands a little bit behind your back. But the payoff, if you can prove these things in the restricted proof system, is that for free, by turning a crank, okay, subject to small technical conditions that Mabod will be annoyed at me if I don't say something about, subject to small technical conditions, but pretty much for free, you will get a polynomial time epsilon DP mechanism with those same privacy and utility guarantees. Now, I want to be clear right off the bat, this mechanism, it will not be your original exponential mechanism based algorithm, right? It's not something it's not a sampler for the distribution that you started with. What it will do is replace that distribution with some other distribution that is efficiently sampleable and maintains those same privacy utility guarantees. So that's the 10,000-foot view. I understand that sounds like black magic, and the purpose of the next 25 minutes is to try to show you why it's not black magic, and maybe give you some example, some simple example. Okay, questions so far about the very high level picture of what we're trying to do? Cool. So here's the plan for the rest of the talk. I'm going to leave privacy for a couple of minutes and talk about convexity. And then I'm going to talk about this tool called the sum of squares method. And then if we get there, which hopefully we will, I'll give you a little flavor of things via an example, which is some mechanism based on high-dimensional histograms. And then in the next talk, Mabod will give us an extended example of how to use sum of squares exponential mechanism in the context of estimating the mean. Okay, so let's switch gears. Let's leave privacy behind for a second. I come from the field of algorithms, actually, And the particular perspective that I take on algorithms always involves convexity. So I come to sing the gospel of convexity. What do I mean by optimization? Here I mean something extremely broad. Optimization is just what you're doing when you want to minimize or maximize some function over some set. And the settings that I'm thinking about, the set S is large, like it lives maybe in high dimensions. And so x really consists of a bunch of variables, x1 through xn. And the function f is multivariate, of course. Now, this can capture all kinds of stuff, obviously. I come from a theoretical computer science background, so I love cut problems in graphs, min cut, max cut. You can look at for the maximum satisfying assignment to a constraint satisfaction problem, but of course this shows up in statistics as empirical risk minimization and all kinds of other things. This is a basic tool. Now, optimization problems that show up in theory and in practice are frequently computationally hard. Often this is captured by NP hardness, but of course we don't just give up. There's lots of things that you can do if you're faced with an NP hard optimization problem. Now, one thing you can sometimes do is apply heuristics, of course, but just as in privacy, we're not willing to go with heuristics in some settings because they will lose our provable privacy guarantees. As a theoretical computer scientist, I'm not willing to go with heuristics for optimization because I'll lose provable guarantees on my algorithms. So once you've decided that you're not going to go with heuristics, that you're going to shoot for provable guarantees, the most important tool in the toolbox is convex optimization. So convex optimization is what you're doing when you have a function you'd like to minimize, and you're minimizing it over some set, and that set is convex, and that function is convex. And as a reminder for what convexity means, for a set, it just means that every 2 points in that set can be connected by a line that stays in the set. And for a function, it means that the area above the curve is convex, or you can talk about second derivatives or whatever, but this is a convex function. Probably you all remember that for to minimize a convex function, you can roll down the hill. And that means that this is a computationally easy problem. Okay, I didn't specify it completely. You need minor additional conditions on f and s to really prove that you can solve problems like this in polynomial time. But basically, if you can get yourself a convex optimization problem, unless you've done something really crazy, you're going to have a polynomial time algorithm to solve it. Okay, but we were talking about hard optimization problems, and hard optimization problems almost by definition are non-convex. So how do we use convex optimization as a tool to handle non-convex problems? In computer science lingo, we relax, or really in optimization lingo, we relax. Relax means that you take your hard optimization problem, some non-convex function f, maybe some non-convex set s, and you replace them with some convex proxies. And then you prove that whatever properties of your optimization problem you cared about before are preserved by your convex proxies. So now you have a convex optimization problem which has the key properties that you cared about from your non-convex one. And this is like an extremely common technique, right? So let's just see a couple of examples from theoretical computer science. These are probably not the simplest examples that there are, but there's like Goemans-Williamson max cut algorithm is a very sophisticated version of convex relaxation that relaxes a quadratic program to a semi-definite program. Vertex cover relaxes an integer program to a linear program. In statistics, we have compressed sensing, which relaxes the notion sparsity, which is basically a non-convex notion, to the one norm. The same is going on in lasso regression. Matrix completion relaxes rank to trace norm. So this is a universal idea, and it's extremely powerful, right? All of these things are highlights of algorithms for optimization in statistics. So the gospel of convexity, this most important fact in optimization, that convex minimization problems are easy, it has an analog in sampling. Remember, I'm going to now walk us back towards privacy and the exponential mechanism. And the basic hard thing that shows up in exponential mechanism is these hard sampling problems. But there's an analog of the gospel of convexity, which is that certain probability distributions built out of convex objects are polynomial time sampleable. What are those distributions? They're called log concave. They're distributions with the following form. So first of all, their ambient space is some convex set. So think a convex subset of Rn. And their probability density function is given by x, or is proportional to x of minus a convex function. Minus a convex function is called a concave function. So if you take the log of the probability density function, you get something concave. That's why it's called log concave. And subject to minor technical conditions, log concave probability distributions are polynomial time sampleable. So we love it if we can design an exponential mechanism-based algorithm which arrives at a log concave distribution at the end for its sampling problem, because we're going to get a polynomial time algorithm. And by the way, not just polynomial time, like these things, especially because of recent progress on deep conjectures in convex geometry called the KLS conjecture and some related ones, there should actually be really fast algorithms for these problems. We're still getting to the point of having them, but they should exist. Fast means like linear time or nearly linear time. So this idea, I want to be clear, is not totally new to privacy. This was previously employed in at least one highly cited paper by Basile Smith-Okurta almost 10 years ago for doing private empirical risk minimization. But in their setting, they basically were doing empirical risk minimization over convex hypothesis classes and with convex loss functions. And what that meant is that when they designed their DP mechanism, their exponential mechanism, they just sort of automatically arrived at a log concave sampling problem. And we're going to be interested in settings where you don't automatically arrive at a log concave sampling problem, and you need to do something to get yourself a log concave sampling problem. Okay, so I've now introduced the two key players, the exponential mechanism and the gospel of convexity, and the idea of relaxing hard non-convex problems in optimization to easier polynomial time solvable convex problems. And the whole idea is just to marry these two concepts. So combine log concave sampling with the idea of convex relaxation to implement exponential mechanism-based algorithms. So a little more concretely, suppose you had your mechanism design problem. You came up with some score function and some set of outputs, and shoot, it's high dimensional and non-convex, and you don't have an algorithm to hand. So what are we going to do? We're going to replace both of them with some convex proxies. Actually, I should be saying concave unless I'm talking about minus the score function, but forgive me the inaccuracy. You will replace both of them with some convex proxies, and then we will just hand off to a log concave sampling algorithm to sample from this distribution. So now I have a different distribution, right? It's over a different set, S prime instead of S, and it's using a different score function, F prime instead of F. So we need convex relaxations which preserve the key properties of the score function and the output set that we started with. What are those key properties? Okay, well, the key property number one, to get privacy, you need stability of the score function. And here I've just baked the epsilon parameter into the stability so that I can avoid writing so much. But you need this bounded differences stability property of the score function. And you need utility, which is a little bit squishier here, but it says that one, if the score function is large, where large is whatever the number is that comes out of the usual exponential mechanism analysis, then you found a good output with respect to your input. And two, that the mechanism itself, the distribution puts a lot of mass on these large valued score functions. Okay, so those are the key properties, and we'd like to maintain those properties when we replace our non-convex hard sampling problem with an easy polynomial time one. So eventually, the idea is going to be to use some state-of-the-art technology coming from convex optimization called the sum of squares method for designing convex relaxations with the right properties. But before I get there, I want to show you a really baby example just to get a flavor of things. Okay? So I don't want to make any claims that this example leads to a very interesting algorithm. It doesn't. I just want to show you some pictures so that we can make things a little bit more concrete. So suppose I want to do the world's most basic thing. I want to release the result of one query on a data set, just a real valued query on a data set, right? So I have some query function Q. It maps data sets to real numbers in some range. This is not a high dimensional problem. This is well studied and completely solved. All right. It's completely solved in the sense that the classic result here is that if you just add some Laplace noise whose size depends on the sensitivity of your query, you'll get an epsilon dp algorithm. No big surprises. But let's forget that we knew that result for a second. And let's imagine that we set ourselves the following goal. Seems natural enough. It's some kind of confidence intervals type of goal. I want to release some value q tilde such that q tilde minus q is less than some interval size eta, say with high probability 0.99 or something. So I get 99% confidence. And a natural way to do that would be, if I didn't know about this Laplace mechanism stuff, I would define some score function over the space of all possible outputs q tilde in the range, say, minus r to r, which is just where the score of an output is just the indicator that it's in the right interval. So the scores are 0, 1 valued. They're not very sensitive. And then I can scale it by my privacy parameter if I want. So if we look at the distribution that we're going to get, we take the out of exponential mechanism, we look at our score function and see, is it concave? Is it good for us? Are we going to get an easy sampling problem? Now, okay, you can solve this sampling problem without using log concave sampling. It's one-dimensional, but there are high-dimensional analogs of all of this, right? This is just for example. Of course, this is not concave, right? This is not a concave function. So what are we going to do? Well, here's one example. I just cooked it up of a concave proxy for this function, right? I made it up. I didn't do anything principled to cook it up, but it's a concave function. And the reason that I cooked this one up is that it leads to a very familiar looking algorithm. Up to scaling and truncation, this proxy is just minus the absolute value of the difference between the thing I wanted to release and the output candidate. And that means that if I use this concave proxy, I just get back the Laplace mechanism. Again, up to some scaling and truncation stuff. Okay, so this is just to convince you that this perspective can recover things we already know about. Questions? Okay, either I'm very clear or very boring, but all right. So to really carry, let me back up. One more thing about this concave proxy. It's not very good. I mean, it's great. It gives you the Laplace mechanism, which is very useful. But it's not very good in the sense that I didn't actually really preserve a lot of the important properties of my of the exponential mechanism thing I started with, right? This guy, this score function, its sensitivity is totally independent of the sensitivity of the query function q, for example. And that leads to a really strong privacy guarantee if you use this score function. And then when you relax to this particular concave proxy, you actually lose that property. So it's actually not following kind of the rules that we're hoping for. It's not, in the sense that we're talking about today, it's not a very good concave proxy because it didn't preserve one of the key stability properties of the score function that I really wanted to use in the first place. So our goal is to design better ones. I'm actually going to leave this problem behind. But our goal is in general to design better proxies that do preserve such properties. And for that, we're going to rely on this method for designing convex relaxations called the sum of squares method. So now I'm going to switch into part 2 of the talk. What is the sum of squares method? Or I'm going to start abbreviating it to SOS. SOS is a few things. The first, most mathematically concrete thing that it is it's a hierarchy of increasingly strong, increasingly tight convex relaxations obtained from any non-convex set in, let's say, Rn, that's defined as the set where a whole bunch of polynomials are simultaneously non-negative. So these are some multivariate polynomials with real coefficients. And this is the set where those polynomials are all non-negative. It's called a semi-algebraic set in optimization lingo. It can, of course, be non-convex. It's the intersection of a bunch of crazy regions. And SOS gives you a hierarchy of relaxations. At the top of the hierarchy, you get the convex hull, which is the tightest possible convex relaxation. But as you go up the hierarchy, the computational complexity of dealing with the relaxation gets higher and higher. So the hierarchy has levels indexed by this parameter called degree, and why it's called degree will be clear in a minute. And if you have an n variable m in a m polynomial set, then the dth level of the hierarchy can be dealt with computationally in n times m to the O of d time. Okay, so if you want, and by dealt with computationally, I mean that you can do things like find a point in the set or optimize a linear function over the set, all the stuff we like to do with convex sets. So at this generic level, these are slow algorithms. I mean, if d is constant, which is what we want, we'll get polynomial time, but it's a slow polynomial. So you don't really want to be doing this on your computer for any interesting values of d and n and m if you're doing it generically. But in many applications, once you understand that there's a polynomial time algorithm based on these ideas, then you can open the box, open the black box, and you can tinker with it to get the running times to be reasonable. So this is just the generic statement, but you can get faster algorithms in many cases. Now, why this? Why these semi-algebraic sets? Well, polynomials are like a universal mathematical language, right? Polynomials are just super expressive. And so if I have, polynomials, they're interesting in their own right, but also, almost whatever combinatorial, continuous, whatever problem I'm interested in, I can almost always either approximately or exactly express it in terms of polynomial inequalities. And then I can use this technology. So that's the first thing that the SOS method is. The second thing is these convex relaxations, okay, they turn out to be large semi-definite programs, and it's pretty mathematically challenging if you just work with them directly to argue that they have any interesting properties. And so we need a sort of technical toolkit for arguing that this relaxation has such and such a mathematical property. And SOS provides a technical toolkit for arguing about these relaxations via convex duality. We'll see it in a moment. The main tool is called the SOS proof system. It's a certain restricted proof system that lets you make arguments about the convex relaxations. I'll clarify in a second. And the third thing that it is, and this is non-technical, is it's a set of philosophies for algorithm design. And these first 2 points, they're maybe like 20-ish years old. And this third point is maybe only 5 to 7 years old. And arriving at a good set of philosophies, a good set of techniques to use the technical tools has been revolutionary in a bunch of areas of algorithm design. So in the last 5 to 10 years, this SOS method has been a huge algorithm success in a wide range of areas: combinatorial optimization, continuous optimization, quantum information, optimal control theory, my personal area, high dimensional and robust statistics, crypto analysis. The list is like just growing by the month, right? So this has been a huge algorithm success because these convex relaxations are so powerful and because we have relatively simple tools to argue about them. So just to give you some idea of applications that have been pretty cool, within combinatorial optimization, we know, subject to some conjecture called the games conjecture, which is one of the most important conjectures in computational complexity, we know that sum of squares provides the optimal polynomial time approximation algorithms for constraint satisfaction problems. If you want to know what that means, find me afterwards. Within robust statistics, there's been a recent algorithmic revolution in robust statistics that some of you may know about, in which we now know polynomial time algorithms with optimal rates, optimal error rates for a whole bunch of high-dimensional robust statistics problems: robust mean estimation, robust covariance estimation, robust regression. There's also, this is in the non-robust setting. Actually, also in the robust setting, we know, matrix completion is an instance, like matrix completion via the trace norm can be viewed as an instance of the sum of squares method, and so on. So there's a million applications of this, and what we're doing is bringing some of the power of these ideas to DP algorithm design. Okay, so I have to tell you now about point 2. The sum of squares proof system, in order for us to put the pieces together into SOS exponential mechanism and for everything to make sense. So what are the technical tools for arguing about this hierarchy of convex relaxations? Well, first of all, what is a restricted proof system? What does that even mean? A restricted proof system is just a collection of rules for deriving true mathematical statements from previously proven true mathematical statements. Okay, that's all of math. But here, I mean that the rules are quite formal and the statements are expressed in a formal language. And you're probably used, or you maybe have some experience with this going back to like high school geometry, where you would write proofs as a sequence of statements in a relatively formal language. And for every statement, you would need to state a reason, and that reason is basically a proof derivation rule. So sum of squares proof system, it's not the high school geometry proof system, it's a different proof system. The proofs are also expressed in some kind of formal language, which you don't need to worry about. I just wanted to scare you a little bit. But the sum of squares proof system, it only has one rule. So it's actually much simpler than high school geometry. The only rule is that squares of polynomials of real numbers are always non-negative, because squares over the reals are non-negative. Simple rule. So here's the world's simplest sum of squares proof. It's not very interesting, but just to give you a flavor, suppose that I wanted to prove the statement for all real numbers a and b, a squared plus b squared is greater than or equal to 2ab. How do I do it? I take the right-hand side and subtract it from the left. I factor the resulting expression. I get a minus b whole squared. That's non-negative, according to my proof rule. So that's the sum of squares proof system. It sounds super elementary, like how can you possibly prove anything interesting with this? But actually, all kinds of inequalities that we like to use day to day have sum of squares proofs. And not only do they have sum of squares proofs, they have sum of squares proofs using polynomials that have relatively low degree compared to the number of variables in the polynomials. That's going to be important in a moment. So things like Cauchy-Schwarz, actually you can see this is like a baby version of Cauchy-Schwarz already. Things like Cauchy-Schwarz, triangle inequalities, including for p norms or Schotten norms or lots of different norms. Actually fancy things like hypercontractivity of low degree polynomials over Gaussian space or Boolean space, if you are familiar with those. So there's fancy inequalities that can also be proved like this. So once you have all your basic inequalities in your toolkit, now you can kind of just start doing math, right? And as long as you used only inequalities that you know have sum of squares proofs, at the end of the day, you're going to be able to compile your English proof down to a sum of squares proof. So that means you actually have a pretty powerful proof system at your hands. Okay, so in what sense is this a technical tool for arguing about the convex relaxations that come out of sum of squares method? Well, suppose I want to prove some property of that relaxation. So what do I mean by a property now? Remember that polynomials are this really expressive language. And so this is actually not quite how we typically think of it. I'm lying a little bit, but I think it's conceptually reasonably clear, I hope. So I have some SOS relaxation of some system of polynomials, P1 through Pm non-negative, right? This is some non-convex set. And suppose I want to prove some property of this thing. And I'm going to express a property of a set as some other polynomial being non-negative everywhere on that set. Polynomial is very expressive language. I have some property of interest. I can often express it in this way. Some polynomial is non-negative everywhere on that set. So suppose not only that I have some other polynomial q that is non-negative everywhere on my set, suppose that I can prove that fact, that when these guys are non-negative, also q is non-negative. Suppose I can prove that fact in the restricted proof system, like in the proof system using only squares of polynomials of degree up to d. So I didn't use all of math. I tied my hands behind my back to prove this. The payoff is that this property of the non-convex set is preserved under relaxation. Okay? So not only is it true that every x where p1 through pm are non-negative also have q non-negative, it's actually true that every x in the dth level SOS relaxation of p1 through pm non-negative will have q non-negative. Okay, the sense in which I'm lying is that the relaxation, it lives in a lifted space of variables, so there's not really x's, there's like some other higher dimensional objects, but let's just not worry about it. This is conceptually what's going on. So now we can see that there's a trade-off. As I ratchet up this degree parameter, I said that the relaxations become more complicated, but also they're tighter. They're tighter in the sense that more properties of the underlying non-convex set are preserved by relaxation. Why are there more properties preserved by relaxation? Because whatever properties are preserved are the ones that I can prove in the proof system, and the proof system is getting more powerful. I get to touch polynomials of higher and higher degree in my proofs. Questions? Yeah, Salil.
You had
Oh, yeah, I mean, it's an if and only if when you get, so, okay, this is all under the hood convex duality for those of you who are okay with that. So these things are primals, these proofs are dual, the proofs are duals. And it's an if and only if when you have strong duality. Actually, it doesn't turn, like, not every polynomial system will lead to strong duality. You need a few technical conditions. But when you put a few technical conditions on the p's, you'll get strong duality, and then you'll get an if and only if. So the if and only if, by the way, means that this, like, that would mean that not only is it the case that every property that you can prove in degree SOS holds for the relaxation, but that that's a complete proof system for the relaxation. That, like, there are no, that if you have a property that holds true in the relaxation, it has a sum of squares proof. That's usually true in applications that we care about, because usually we get strong duality. Okay, so back to our 10,000-foot view. I said that SOS exponential mechanism, the idea is that you wanted to run exponential mechanism, let's say, over a convex output set. And suppose that you can prove privacy and utility in this restricted proof system. Then I said you get a polynomial time algorithm with the same privacy and utility guarantees. How does this work? Let's put it together. Start with the exponential mechanism that you cooked up for your privacy application, and it's not necessarily computationally easy, right? It's got some non-convex score function, but actually I'm going to need to assume, and this is something that we'd really like to address in the way that we think about SOS exponential mechanism right now. I'm going to assume that even in the sampling problem you start with, that the region of outputs is convex. And maybe at the end I'll say why I need that assumption right now, and we don't have good ideas of how to remove that, but I think eventually we will. And suppose that I also have degree d sum of squares proofs of stability and utility for this exponential mechanism instantiation. Then what's the natural thing to do? I said I wanted to replace non-convex things with convex proxies. The non-convex thing here is the score function, so I'm gonna replace it with a convex proxy. Now, I told you about sum of squares relaxations for sets. I didn't tell you about relaxations for functions, but it's not too hard a leap, because, you know, a function is convex if the region above it is convex or concave. So, okay, there's a way to talk about SOS relaxations for functions. And then I'll hand the whole thing off to a log concave sampler. And if I manage to do everything in degree d, I'm going to end up with something like, if n is like the number of variables or the dimension of the underlying sampling problem, I'm going to end up with something like an n to the O of d time sampling procedure for this relaxed exponential mechanism that will maintain the privacy and utility properties of my original one. Okay, so I'm going to try to take only at most 8 more minutes or something, so that maybe 9, so we get a bit of a break. And Mahbod is really going to give us the main example of all of these ideas that I've made very abstract and incomprehensible, so he can save us. But I want to give you a small taste, again with a simple but less simple than before algorithm. So I want to discuss a very basic algorithmic primitive. Actually, it's one that we use under the hood in our mean estimation algorithm for kind of an initial guess at what the mean of a distribution is given some samples. It's basically just an algorithm to localize a bunch of points in a large space. So let's imagine that you have some points x1 to xn, and they live in, oh dear, I used d. Okay, this d is dimension, and I really apologize that d previously meant degree. They live in, say, minus r to the d, and r is like really big compared to where the points are. So I'm thinking of the points as mostly being contained in some small region, like maybe most of them are in a ball of radius 1. But all I know about them a priori is that they live in this really big region, and I want to kind of localize them. I want to find some point nearby, and I want to do it in a private fashion. So the claim is that there exists a polynomial time epsilon dp algorithm which takes these points, and I might have screwed up my constants here a little bit, but with high probability, it'll find some other points in minus r to the d with such that it's close, where close means constant distance, to, let's say, 90% of the x's, provided not just that such an x exists, but that a slightly better x star exists, where slightly better means, I didn't put it on the slide, means that it's within distance, let's say 1/2 instead of 3 to 99% of the xi's. So I'm going to lose a little bit in my constants, but I'll be able to localize to a region that contains a lot of my points. And of course, I need the number of points to be sufficiently large, and the size is not going to be that surprising. It's like the log of the volume of this region divided by epsilon. Okay, so the claim is there exists such a method. Actually, probably there's lots of ways to come up with something like this. It's not that hard a problem, but I want to show you how you might do it via SOS exponential mechanism. So what's the natural exponential mechanism without worrying about polynomial time? So just to restate my problem, I want to map x1 to xn to some other point x such that, oh, I lost the 90%, such that x is close to most of the xi's. Well, the natural thing to do would be just to use a score function that counts the number of xi's that a given little x is close to, right? So my score function is defined over the whole output space. It's minus r to the d. And for every point in minus r to the d, I just assign the score of how many xi's are you close to, right? And so then I'm going to get back, if I have, if I do the usual analysis, I'm going to draw a sample from the, the exponential mechanism distribution. I'm going to get back some little x, which is close to 90% of the xi's, if something like that exists, which means like if opt is large enough. So no big surprises here, but this is some nasty non-convex function. I mean, how the heck are you going to sample from this distribution in high dimensions? So now I'm going to make you read a little bit of math, but I promise only for 5 minutes, and then it's the end of the talk. The first thing, I just want to give you a flavor of what goes into the construction of the SOS analog of this exponential mechanism. And the first thing to do is I'm going to express, I need to, I said that polynomials are like a good universal language. Okay, I got to use the language. I got to translate my non-convex function into something about polynomials. So here we go. So this score function, it depends on the data set, capital X. It assigns values to little x's. I guess it's hard to tell the difference between my capital X's and little x's, sorry. It assigns values to little x's. It's the number of big x's that the little x is close to, and I really screwed up my constants, I apologize, but here we'll just use 1. And let me express this as a polynomial optimization problem. So here's the problem. It has variables, let's say b1 through bn, where there are n is the number of big xi's. And I'm gonna set up constraints in my polynomial optimization problem so that those variables represent 0, 1 indicators of whether little x is close to big X. Okay, so here's how it's gonna look. First of all, to make these things be 0, 1 indicators, I'm gonna impose the constraint that for each I, bi squared is equal to bi. Okay, I talked only about inequalities, and this is an equality, but you can express an equality with 2 inequalities, so no big deal here. And you can see that the only real numbers which satisfy b squared equals b are 0 and 1. So this forces the b's to be 0, 1 indicators. And now I'm also going to ask for the following constraint. bi times the, let's say, square distance between xi and x is at most 1 times bi. Okay, there's a few things going on here. Y the square, some technical thing, because I would really like this to be a polynomial in little x as well. And the square Euclidean distance is a polynomial. The ordinary Euclidean distance isn't. It has a square root. Don't worry too much about it. What's going on here? Well, if bi is set to 0, this constraint is like 0 less than 0. It doesn't do anything. But if bi is set to 1, this constraint expresses that little x is within distance 1 to big xi. Okay, so now I've got some constraints. I've basically built myself an integer program just out of polynomials. And now, in order to get it to equal this sum, I'm going to maximize the number of bi's that I can flip on. Right? I want to flip on as many bi's as possible. I want to flip on the ones that satisfy this constraint. So I expressed this function as the optimum value of a polynomial optimization problem. Again, it's not that surprising that we could do this. Polynomials are very expressive, but here's how you could do it. There's probably other ways to do it as well. So now, I'm going to show you a sketch of an SOS proof of utility. Okay? By sketch, I mean I'm not going to show it to you literally in the formal language. I'm going to do it in sort of a hybrid between the formal language and English, because it's just too impossible to, on a slide, decipher all the formal stuff. But the important idea here is going to be that you can use the only inequality that you have to use in this proof has an SOS proof. It's just the triangle inequality. And therefore, I'm going to be able to turn the proof into an SOS proof. So let's do it. So what does utility mean? And again, I really apologize for screwing up the constants. But what does utility mean here? Utility means that if you have a high score, then you're close to a lot of xi's. Okay, and here's how I'm going to express that. Well, I needed to assume, in order for the utility guarantee of the algorithm to make sense, there needed to be some point that is close to a lot of xi's, some high scoring point. So let's let x star be that point. Let's let x star be close to 99% of the xi's, where close means distance 1. And my goal now is an SOS proof that if x has high score, like score at least 0.99n, then x is close to x star. If x is close to x star, then by triangle inequality, because x star is close to a lot of xi's, x will be close to a lot of xi's, where I'm just losing factors of 2 in the constants everywhere. So I want to build an SOS proof of this, because then my SOS relaxation of my polynomial optimization problem, if I use that as a score function, is going to give me an SOS exponential mechanism which preserves the guarantees I want. Okay, I know this is the most math I'm going to make you read, and we'll do it slowly. And I'm dropping the convention that I need to square the norms to make them polynomials, because I said I'm doing it in a hybrid of formal and English, and I didn't want to deal with the squares. But in real life, you have to keep things as polynomials. Okay, here's the steps of the proof. I want to convince you that all I need is triangle inequality. I'm going to take this thing I want to upper bound, x minus x star, the distance between the two of them, and I'm going to express it in terms of the individual points, the xi's. So how am I going to get there? I'm going to sum over all of the points where x star is close to that point. So all the points that are in this local region that I want to find. I'm going to sum over all those points, and I'm going to just look the summation of these indicator variables, bi's, divided by the total score. So this is some number less than bigger than 1, or equal to 1. So this is a true inequality. I just replaced 1 here with this ratio. And now I'm going to do the normal trick that you want to do for triangle inequality. If you want to use triangle inequality to bound the distance between 2 points by comparing them to a third one, I add and subtract that point. So for the ith term in the sum, I'm just going to add and subtract the sample, or the point xi, in my norm. And now the only interesting step of the proof is triangle inequality. I'm gonna use triangle inequality to say that this expression is at most little x, the guy I'm trying to argue about, minus xi, plus x star, the guy I know about, minus xi. Okay, and now I had, well, let's deal first with the x stars. These numbers are all at most 1, and I'm dividing by sorry, I think I screwed up a normalization here. Well, if you don't make me do it live, I apologize. The point is, these numbers are all at most 1, and it's easy to deal with, and these aren't even polynomials anymore, because these are just numbers. X star is something I know about, xi is something I know about. This is the guy I'm trying to argue about, but I had these constraints that said if the bi's were turned on, then little x minus capital Xi was at most 1. So I'm going to use those constraints to upper bound the portion of this sum coming from here. And at the end of the day, I'm going to conclude that this whole expression is at most 2. I don't expect you to have followed this formally. I'm just trying to make the case that if you want to establish these just sort of simple geometry arguments, this point's close to this one, this point's close to this one, do triangle inequality, everything's going to be fine if you want to do it in a sum of squares fashion. Okay, so if you want to get the real version of this proof, corner me afterwards. Proving stability is actually easier than proving utility, so I'm not going to worry about it, but sum of squares proof of stability is really not hard. So that's the most that I want to show you of how to prove this theorem using SOS exponential mechanism. But if you formalize the arguments I just showed you and you plug it into the SOS black box, out the other side comes a polynomial time sampler. Yeah? Yeah, good. Good. Okay, the volume part of utility, yeah. So this is actually why right now we need to start with the set we're sampling from being convex already. Because I actually don't know how to, like, what you'd like to do is start with a set that's non-convex and relax that set as well using SOS. And the problem is that we don't have good tools to argue about the loss in volume when that happens. So the volume piece kind of stays. You don't really even need to do anything because the set that you're working with kind of stays the same. Actually, in this new work with Chris at MIT, this work on sparse mean estimation, we do have to do a little bit of convex relaxing the set, but we kind of do it by hand. We actually don't know how to argue about the volume of the SOS relaxations. So that's actually a pretty interesting direction to look research-wise. Okay, so I think Mabad's going to be mad at me if I don't make a disclaimer. So don't read this, don't read this. This is just to tell you that there are some technical conditions that I didn't tell you about. Don't worry about them. I can tell you what they are if you want offline. They're not a big deal. They're just that you need, basically you need polynomials that don't involve crazy huge coefficients, like exponentially large coefficients. That's not good for algorithms. They don't like that. They're not good at dealing with numerical precision issues, stuff like that. Stuff that does not turn out to be a big deal. But I wanted to make sure that you know that I'm not like a snake oil salesman, and there are formal theorem statements that capture these things and put the right technical conditions in place. Okay, so that's all I've got. Thank you for your attention. I know I made you listen to a bunch of abstract stuff. I really appreciate your time. If you have questions, I'm happy to take them.